So thank you for the organizing committee to give the chance to present my work in this workshop. So today we are talking about mixed finite element approximation for poroelasticity. Is basically funded by EPSRC, SERV, and also Institute IIT Roorkee. So my talk basically is divided in two parts. In the first part, will focus on robust a posteriori analysis for poroelasticity in deterministic point of view. This is actually joint work with David Sylvester. And the second part, we will see that what will happen that we are going to solve PD with uncertain input and how we will solve. So here we will try to discuss solvers to solve this such big system. This is actually joint work with Catherine Powell. So let's start our first contribution. So my voice is audible to everyone and clear. My voice clear to all of you. Hello.
Sorry, what did you say?
Yeah, my voice is clear to all of you.
It's okay. It's not perfect.
Yeah. Okay, thank you. So now let's start. The first contribution is the robust a posteriori analysis for mixed FEM of the poroelasticity. So why Biot consolidation model? So in the last few decades, model based on fluid flow and the deformation in the porous media getting a lot of attention because these models have a lot of application in science and engineering. We will talk about basically Biot consolidation model. These have a lot of application in geoscience and as well as medicine. Why locking free mixed finite element method? So basically the locking of finite element method when we are solving either elasticity problem or Biot model, we see that this is a very significant issue in the computational engineering. If you are going to solve some merely incompressible case, we see it is difficult if we are going to solve this conforming finite element method. For example, if we are going to solve linear elasticity problem, where we have to find the displacement, where mu and lambda is a limit coefficient and f is the force function with some boundary condition. And if you will see the structure of mu and lambda is actually again depends on two further parameter. The one is the Young modulus and another one is the Poisson ratio. So when we'll talk about a nearly incompressible case, so mu is actually fine, but lambda actually contains quantum 1 minus 2 mu. So when mu will approach to half, this term actually tends to infinity, and we will solve using some conforming finite element method. We actually face this locking thing and we will not get correct displacement. So to resolve this, one of the scientists is Hermann introduced one formulation, which is called Hermann formulation. Hermann introduced one pressure term instead of this divergence term, and then he introduced another equation which actually represent the relation between divergence and this pressure term. And he claimed that it actually robust with respect to nearly incompressible, as well as if you are also going to limit case nu is equal to 0.5, this formulation actually converts to Stokes case. Why a priori are not enough? So basically, when we will talk about the a priori, we always get some error u minus uh is bounded by some mesh size h of s, and as s tends to 0, we assume this error also tends to 0. But here always the constant will depend on the exact solution. So basically, we will always talk about asymptotically that error is decaying with some rate. We will not get the actual information of local size of error. And if solution has some singularity, local singularity, it deteriorates globally. Like where solution has some intent corners or interiors or boundary layer, we see that we will not get a good accuracy. But we always try to define some indicator in a way that which are capable to give the information of the local size of error. So we actually move to derive some a posteriori estimation, where we'll try to find some neta which actually depend on computed quantity and we'll try to find reliable bound as well as the efficient bound, where we can say that this estimator actually is capable to give the information, and whatever information we are getting, it is reliable as well as efficient. And we will use this information and try to construct the algorithm in a way that will get our accurate solution with minimum number of degree of freedom. Why robust aperture estimation? So one is thing that when we'll talk about the aperture estimation, first we'll try to think about to drive aperture estimator. But when we are solving problem which have a lot of parameters, then we have to careful that whatever estimator we are talking is robust with respect to parameters or not. So Biot consolidation model actually depends on many material parameter, and ensuring robustness is very important. Maybe, for example, what happened for one particular parameter choices, maybe your efficiency is very close to 1. But what happened that if you are changing for example, in Poisson ratio, we are seeing that if you are choosing some 0.4, maybe your estimator works well. But if you are going to choose 0.49 or something, then maybe your efficiency is more than 100 or more, maybe more than this. And it also happens, same thing, if you are going to solve, if you are trying to talk about solver point of view, the same case happen. Maybe your iteration count will be near to 100 or less than 100. And when you are going to nearly incompressible case, the iteration count actually drastically increase, and it may be more than 1,000 and maybe more than 2,000. So robustness is very important if you are dealing with problem with lot of material parameters. So this is our Biot consolidation model, where we need to find displacement of elastic medium U and the pore pressure PF, which satisfy this equation, where sigma is directly coming from this elasticity part with coupling of the fluid pressure alpha PF, and alpha is the Biot constant, and lambda and mu we already know that these are the young modulus. Lemma coefficient, which depend on this Young modulus and Poisson ratio. And the same things we also feel here if we are talking about the nearly incompressible case, where we see that the same condition we face here and how to solve. So if we are going to use Harman techniques, if we are just using this lambda divergence dot u, will just replace by Harman pressure. Then what will happen if we are talking about the existential uniqueness of this problem? Then we need to maintain two in-sub condition. First in-sub condition with this lambda divergence dot u, and the second in-sub condition with this fluid pressure. And it is difficult also in the continuous point of view, but it is more difficult in the discrete point of view, where you are going to choose some finite element choices, mixed finite element choices, where we see that we have very limited choices. Mixed finite element, and maybe it is very difficult to generalize also. So what we will do that we'll actually try to go some known three-field formulation, where what happened that they define, instead of Harman pressure, they define total pressure, and which actually not only depends on this divergence term, it also depends on this fluid pressure. And then write another equation which represents the relation between this divergence term, fluid pressure, and total pressure. And they claim that now, if you are going to prove this existential uniqueness, you don't need to maintain in-sub condition with two pressure. You just need to maintain in-sub condition with displacement and the total pressure. So now we are free to choose the finite element choices for fluid pressure. There are two references. The first references actually where they discuss about the a priori for this poroelasticity, and the second references we discuss about the solver for deterministic Biot consolidation model. And here there are two applications where we see the ranges of this Young modulus, Poisson ratio, and the permeability. If you will see that the Young modulus actually vary from 1 to 68 in the soft tissue of central nerve system. Poisson ratio actually vary from 0.3 to almost 0.5. Permeability 10 to the power minus 14 to 10 to the power minus 16. And there is another application in geophysics where we see that the E actually order of GPA, Poisson ratio from 0.1 to 0.3 or 0.4. Permeability 10 to the power minus 9 to 10 to the power minus 21. And mu, if in particular, if we will talk, is very large. So if I'm dealing with such type parameter, we are going to solve, then if our estimators is not robust, then we will face a very difficult situation. So now we'll try to discuss first the weak formulation, and then we will move to derive our a posteriori estimator. So for weak formulation, we define some well-known spaces, some L2 spaces, and some Sobolev spaces. And then we define the Sobolev spaces for our displacement, where we will just take the collection of H1 and we'll restrict on the boundary is 0. And similarly, we define for the fluid pressure XP. When we have these function spaces, we can write the weak formulation, find UPTPF, satisfy this weak formulation, and the definition of this bilinear form is given by this. And now we'll write the compact form because we want to prove the beta stability result. So write in compact form, and it is easy to write, and we can also prove. Now we'll try to discuss norm corresponding to this beta stability result. And here we'll use the parameter dependent norm because we are talking about the robust estimator. Then we have to use this parameter dependent norm, which actually ensure the robustness with respect to this parameter. And if you will see, the motivation to choose this norms directly come from our bilinear form, displacement, and also this total pressure and the fluid pressure. Now we will discuss some well-known result. The first one is the Kohn inequality, which actually gives the relation between this Cauchy stress and this gradient norm. And the second one is the well-known Insup condition. And the third one is just the continuity result of this bilinear form A. So we'll discuss first a well-posedness result first, where we will prove this beta stability for any UPTPF belongs to some suitable XQ and XP spaces, and we'll find the triplet VQ2PF which satisfy this lower one. This is one type of Insup condition. If we can write and also write in different way. If we have this well-posed result first, we can easily prove well-posedness result second, just using the definition of this bilinear form, and we can prove this existential uniqueness result. So we are using this symbol. The symbol means that these are independent of the mass parameter as well as Lemay parameters and Biot parameter, and also this permeability law. Then we will move to define the discrete spaces. So we are actually only talking about the conforming finite element spaces here, and we are not talking about any non-conforming and discontinuous Galerkin types. So we'll divide our domain into subdivision TH, where we are taking regular, rectangular, or either or triangular cell K, and then we define mesh size HK, and then we define the set of EH. Because we are using the conforming mixed finite element spaces, so we'll just choose XHU, which is nothing but the subset of XU, and we'll choose suitable MH, which is also subset of L2, and suitable XHP. And when we have discrete subspaces, we can write discrete weak formulation. And here we are not going to discuss the well-posedness result. We just need to ensure that this displacement and this total pressure subspaces actually just satisfy this discrete Insup condition. And if it satisfies, then it's automatically the problem is well-posed. And the proof is similar as we discussed for this continuous one. So here we'll just try to discuss some possibility. For example, we are going to use a Taylor-Hood element Q2, Q1, Q2. So we know that this Q2, Q1 already satisfy this Insup condition, and we can use, and this will be well posed for our problem. We can also use, instead of this, P2, P1, P2 on the triangular element. So Q2, Q1 and P2, P1 is like that. We are using, this is the 9 degree of freedom, and this is Q1 is 4 degree of freedom. Similarly for P2, P1. We can also go for any Taylor-Hood stable element. And there is another question. Can we extend this to lowest element or not? Because sometimes engineer only interested this lowest order element. So yes, we can extend this idea for to lowest order element like Q1, Q0, Q1 and P1, P0, P1. Just we need to add one stabilized term, and then we can also use, then whatever we are talking, actually we are talking about very general sense, whatever finite element we will use, either Insup stable or like this Q1, Q2, Q1, Q0, Q1. whatever we will talk, it will be applicable for all these possible approximations. So now, what is our aim here? To develop robust error estimators, which is actually reliable as well as efficient. So we'll try to find some neta, which is actually is bounded by this, plus some theta. Theta is actually is a data oscillation term. And symbol, I already told you that it means that a constant independent of mass parameter and also independent of Lamé coefficient and the Biot constant and as well as the permeability. And then we'll try to prove some efficiency for our estimator. Then we can say that the convergence rate of this estimator and also convergence rate of our error will be the same. So the possible avenue, either we will try to develop some explicit estimator like residual estimator, as we saw also in the last talk. And another possibility is we can also discuss about the implicit estimator. So we'll start residual-based a posteriori estimator, and we'll define some parameter, as I told that, because we are talking about robust estimator. So we need to multiply some suitable parameters, which actually ensure that our estimator is robust with respect to these parameters. So we'll define some parameters ρ1k, ρ1e, and ρd for our edge residual, interior residual, and also for data oscillation terms. And then we define local error indicators, which nothing but is the contribution of our interior residual, edge residual, and the this relation of this divergence and this total pressure. So in definition of the interior residual is nothing but is RK, and RK, if you will see that, if you recall the PD, so RK is directly related to first equation, and this RK is related to the last equation, and neta JK, as I told that, it actually just related to this total, the relation between displacement, total pressure, and the fluid pressure. And here we are using F and GH, which is denote if you piecewise polynomial approximation of F and G. We can also take possibly discontinuous across element A. Then we define as residual, which actually calculate the jumps between edges. This actually just nothing but is the flux terms coming from displacement and the total pressure, and that this bold RE and this is RE. RE actually representing the flux terms, which is coming from our permeability part. And then we define data oscillation term, which actually represent the error between our actual data and its approximation. Then we'll write our residual estimator, and the data oscillation term is nothing but is the all the local contribution, the sum we will sum up, and then we will define data oscillation term in the same way. And then how we can make sure that the proposed estimator is robust, reliable, and efficient. So we'll drive upper and lower bound with the guarantee that the constant actually independent of mesh size as well as all the parameters of this PD. So we'll prove the reliability estimates. I'm not going to discuss the proof. So we'll prove first the reliability estimate, and then we will prove the efficiency estimate, which ensure that our reliable estimator, proposed estimator is reliable as well as efficient. And also, as I told that, the constant independent of the parameter and mesh size. So our estimator is also theoretically is reliable, efficient, and robust. So the next question, is it possible to develop a robust error estimator which is equal reliable and more efficient in comparison of residual estimator? So answer is yes, we can develop some estimator which is more reliable and is equally reliable and more efficient. So we'll try to move to implicit error estimate. So first we define a Biot consolidation model local error estimator. So we define the error estimator, which is nothing but is the local contribution of this Biot error estimator. And the definition of this Biot error estimator, if you will see, is a triple norm of this, all this error quantity, EVK, E transpose VK, and EFB. These error quantities coming from our PD, all three equations. And if you will see the definition of this norm, is represented by this expression 2 mu, this and other quantity. So is also directly coming from our norm definition. And how we'll compute this error quantity? So to compute this error quantity, we have to solve error equation on each local element. So this is nothing but is our Biot equation. We are solving locally, and this is the error equation related to this Biot problem. So we need to solve this equation to compute this error quantity in some correction spaces Q3, Q3, and then we can compute this error quantity. So the next question, what we are computing, how we can ensure that is equally reliable and efficient and as well as robust. So we'll try to prove upper and lower bound of this problem. So we have two choices. Either we will try to prove reliability with the error, or we already proved our residual estimator is reliable, efficient, and robust. So we can try to make this upper and lower bound with our residual estimator. So we prove this estimate, where we'll try to derive estimators like this is the lower bound with this residual estimator, and we also prove the upper bound. So it ensures that our local error estimator is reliable as well as efficient and also robust, because our residual estimator is reliable, efficient, and robust. And here is constant is also independent of all parameters and mesh for all k in our mesh. So next question, because if I'm going to use this Biot consolidation local error estimator, here's the problem. We need to solve this couple problem on each element. So is it possible to develop the robust estimator that has decouple problem? So answer is yes, we can develop. So we'll try to move the Poisson problem local error estimator, which is nothing but is the local contribution of this Poisson error estimator. And the definition of this Poisson error estimator is nothing but the triple norm of these three error quantity. So to compute these three error quantity, we need to again solve PD. But now we don't need to solve this couple problem. Now we are solving only decouple problem. All equations are independent. We can compute separately. And then the next question, whatever we are computing is reliable, efficient, and robust. So now we have two things. Either we'll try to make relation with error, or we can try to make relation with our estimator, either with residual estimator or Biot local error estimator. So we'll try to prove, we'll derive upper and lower bound with our Biot error estimator, which ensure that our Poisson error estimator is reliable as well as efficient. What is a very appealing feature? So first is we are solving three decouples problem. And the second is if we are going to choose ETP belongs to Q2K. So you will see the second equation is just L2 inner product. If it belongs to Q2K, so we don't need to solve. This is directly equal to this quantity. So second equation, we don't need to solve. So you need to solve only the first and third equation. And the last is you don't need to maintain this stability of this local problem. There is no need to construct compatible correction spaces because we are solving this decouple problem. So now theoretically we already proved that what we are developing this all three estimator are reliable, efficient, and robust. Now I'll try to see computationally whatever we are talking is numerically is also working or not. So we'll discuss two numerical examples. The first one we'll discuss on rectangular element Q2, Q1, Q2, and the second one we'll try to develop some adaptivity mesh. So we'll try to go to use P2, P1, P2 triangular element, and adaptivity we will use the standard refinement loop as we already saw in our previous talk. Solve, estimate, mark, refine. So it is easy. We don't need to discuss again because we already listened to the last talk. What is the mean of solve, estimate, mark, refine? So we'll do in the similar way to generate regular mesh. with mesh size HL. So first we'll discuss with the analytical solution to check what is the efficiency. So we'll take a square domain with zero essential boundary condition, and the expression of U and PF is defined like this. So here you will see that, because as I already mentioned, there are a lot of parameters. So we are choosing three choices of Poisson ratio: 0.4, 0.499, and 0.49999. And for alpha is also we are choosing, this is the Biot constant. So we are taking three possible choices. Alpha is equal to 1, alpha is equal to 10 to the power minus 2, alpha is equal to 10 to. And we are taking kappa is equal to permeability is equal to 1. So we'll take different choices in the different table. Otherwise, it is not easy to mention all the choices here. And H, we are taking different choices: 1 by 4, 1 by 8, 1 by 16, 1 by 30. So you will see that residual estimator, the efficiency is like 2.88, 2.69. So it is near to 2.6 for all different choices alpha. And if I'm talking about the Poisson estimator, this is actually is near to 1, is 1.35, is more efficient compared to the residual estimator. And if I'm going to see for different choices of Poisson ratio, so 0.4, 0.499, and 0.5. So you will see when we are changing these parameters, our efficiency actually is not changing to ensure that our estimator is robust. If I'm going to see different choices of parameter, this permeability 10 to the power minus 5, again, we are getting similar types of result, which ensure that our estimator is robust also with respect to kappa. The third choice is kappa is equal to 10 to the power minus 10. And again, we are getting similar types of result, which ensure that our estimator is robust. And now there are some figure related to this to see what is the convergence rate. So you will see this is our residual estimator, this blue one, red one is the Poisson estimator, and this blue represent the error, and the black one is the rate. So we can easily see that this estimator is parallel to our error plot, and it will ensure that our estimator is reliable as well as efficient for both choices 0.49 and 0.4999. And as we already saw in table also, for different choices of parameters, efficiency actually remains same. So which ensure that our estimator is reliable, efficient, and also robust. So now we'll try to move to a different example with mixed boundary condition, where we want to check that our estimator is capable to detect the singularity and get better accuracy or not. So here we are taking omega is a square domain with this mixed boundary condition. In the half part, I will just choose this mixed boundary, and we choose force function is 1, 1, and G is also 1, 1, and Young modulus is 10 to the power E5, very large value, and alpha is 0.01, and kappa is 10 to the power minus 10. And we see that if we are using uniform mass, our Poisson estimator only decaying with 0.32, the convergence rate. But if we will use adaptive mass, then we are actually getting this optimal convergence rate, rate 1, because we are writing in terms of degree of freedom. So rate 1 actually will indicate that order 2. So we are seeing that our residual estimator is also decaying with optimal convergence rate and also Poisson estimator. Similarly, when we are going to see different choice 0.49999, again is decaying with optimal convergence rate, but when we are using uniform mass, is decaying with 0.3. These are the masses where we can easily see there are a lot of refinement on the corner because of this Dirichlet-Neumann's corner. Here is the singularity, and it is actually easily capable, and there are a lot of refinement, and we are getting better convergence. This is the pressure graph, which indicating there is a singularity on this two corners. So what have we achieved? We achieved the novel a posteriori estimators, which are reliable as well as efficient and robust with respect to all parameters. So these are two references related to this. So first one is the linear poroelasticity, and the second one is just for the elasticity. So the next question that as we know that in general, whatever we are talking about these parameters, so it is a possibility that whatever we are using information, it is not correct. It is some noise will be there or some uncertainty will be there. It is good to see what is happening that if we are going to solve some PD with uncertain inputs. So we'll try to move to second contribution is parameter dependent linear poroelasticity. It is already have three equations. So when we'll talk about this uncertainty inputs, we'll see that maybe we have to face more equation to solve. So we'll start from this deterministic case. And sorry, here we are using different notation for domain D because this is the standard notation of this UQ community. Otherwise, the finite element community will use omega here, but in the UQ community, because omega is actually we use for this to define this uncertainty. So we'll find U, PTPF. We already saw this is the word consolidation model with this mixed boundary condition. And if we are going to choose this Young modulus is uncertain, and also this kappa is uncertain with some finite numbers of parameters, then what will happen that if you will see, if Young modulus is uncertain, then mu will be uncertain, and also lambda will also be parameter dependent and kappa. But the difficulty is this: if we are going to choose, for example, if we are going to choose the representation of E and kappa, like it depend affine dependence of this parameter by k and zk, where we can assume this is the image of independent mean zero and uniform random variable. But we are taking affine dependence, but our three field problem here, lambda is actually occurring here. Because of this, we need, if we are going to solve directly this model, then we need to deal with the non-linearity of the parameter. It doesn't matter, it depends on just affine dependence, but because of this condition we are going to solve directly, then we have to deal with this non-linearity of parameter. And we don't want to face this difficulty because otherwise it is very difficult. If we are going to use more parameter, then it is very difficult to solve this system. Then what we will do, we'll define a novel 5-field formulation where we'll define two pressure term, or you can also say that this Lagrange multiplier P1, P2. And we will use in a way that we'll get this 5-field formulation. And if we are solving this 5-field formulation, we don't need to handle this non-linearity of parameters, because all parameters, if you will see that E is occurring, is only in the equation is not coming in this division part. So we don't need to worry about this non-linearity of E. If we are going to solve this 5-field problem, I have to only deal with this affine dependence of parameters. So this is the benefit, but again, we need to introduce two more equations. So now we have to solve 5-field formulation instead of 3-field formulation. So I'll define some function spaces to discuss about existent uniqueness. So we define some Wagner spaces corresponding to this parametric dependent PD. This L2J, which is defined like this, is the norm vector space with this norm. Then we'll define Wagner spaces for our displacement one, pressure one, and the fluid pressure. When we have this, then we can write our weak formulas. Now it is more complicated. Now we have to deal with this 5-field problem. So U, PT, PF, P1, P2, we have to find, and we have to solve this weak formulas. Write compact form to discuss about the existent uniqueness. So this is the definition of all these bilinear form. And here you will see lambda tilde only depend on the Poisson ratio. So it is the deterministic one. This lambda tilde and mu tilde are deterministic because it just depend on this Poisson ratio, is not depending on E because we separated from E. We are only taking mu tilde, this deterministic part, and other, those are dependent on affine parameters, we'll take separately. Now we'll define our norms to discuss about the Belfort result. And here again, as I'm telling that, if you are talking about this robustness with respect to this Poisson ratio, so you have to choose carefully a norm. Otherwise, again, to solve this problem, we have to face a difficulty. So we'll choose this norm with this weighted norm with these parameters mu tilde and kappa and others parameters alpha. And we prove first well-Poisson result, where we assume if assumption 1 is valid, then we can prove this in some condition or lower bound of this beta stability result. And if we have this beta stability result, we can just use the definition of bilinear form and we can get this our well-Poisson result. Now we'll try to move to discrete approximation. And here, first we define the finite element approximation for spatial part. So we'll choose this finite dimensional spaces for displacement, fluid pressure, and the total pressure. So here, to define these spaces, as I already mentioned that we need to, in the deterministic case, we already saw, we are choosing this BH for the displacement and total pressure, we have to maintain this of conditions. So here we will also choose this finite element spaces in a way which satisfy this discrete of condition. And then for parametric part, we define this multi-indices and then we'll define this approximation, orthogonal polynomials. And then we define our S lambda is nothing but a span of this xi alpha. And then when we have this finite element approximation, parametric approximation, then we'll just define discrete subspaces for our displacement 1, fluid pressure 1, and the total pressure. And when we have this, we can write our discrete 5-field formulation in compact form. And as I told that, if you're going to assume that this discrete choices of BH and WH satisfy this in-sub condition, we can ensure that this problem is well posed and the proof is similar to the continuous one. So now try to write in matrix form and see that how we can solve, because this is very large system. So if we are trying to write in matrix form, we'll get here GK is representing this parametric part and AK or others P1, B2, these are representing from terms coming from spatial part. But from here, we are not getting anything. So we'll just try to rewritten this system. We'll write in this way. So this black, this blue, red part will indicate, we denote by A, and the blue, black part we will denote by B. And then the lastly blue part will write in terms of C. So it will write this compact form. So we'll get write A, B transpose, B minus C. And here we know that how to solve this. So ideal preconditioner is this P, A, S. S is the surcomplement corresponding to this saddle point problem. But it is not practical one. We cannot compute this. It is not computational cost very large. We can't compute, because here you will see that we need to also find the inverse, and this will be the dense matrix. So what we will do, we'll try to go to define some approximate precondition. We'll try to find some approximation of this A and also the approximation of surcomplement. So the choice, we can try to use this mean-based preconditioner. We're trying to find some mean-based approximation of A, and also we'll discuss the approximation of the surcomplement later. But you will see that if we are going to choose this approximation, again, if we are going to compute this surcomplement, then this again will be dense, will not get sparse approximation. So first we'll discuss this, the A approx. So A approx, you will see that A1 approx is nothing but we are dealing with this Cauchy stress tensor. So what we will do, we'll just remove this off diagonal, then we will get better approximation. We just need to maintain this diagonal term, and this motivation directly come from our cons inequality. The second result, so you can write the eigenvalue corresponding to this preconditioner inverse A1 satisfy this bound. The second choice approach 2, we can just take the diagonal entry, then again all eigenvalue corresponding to this belongs to this interval.
So you have about 5
And
minutes left, just to warn you.
Yes. So I'm just going to finish this. So now we'll try to prove the relation A inverse A approx. So combine this result, we will get here, and here you will see bound actually is not depending on nu. It depends on E0 max, E0 E min, but they are not depending on Poisson ratio and this alpha and things. And again, we will just make the relation C inverse C approx one, and we'll get this. Now we'll talk about our Sur complement. So if we are going to use directly this, as I told that it is not the sparse one. So what we will do, we have in-sub condition, and so we'll use this and we'll write this matrix corresponding to this. And here we see that this C tilde is nothing but is the mass matrix, and D naught is the mean part of our D component. So, and here E naught is the pressure E naught dependent mass matrix, and we'll get this eigenvalue one. And again, you will see the lower bound only depend on this in-sub condition, this discrete in-sub condition gamma, and E0 E max. And theta actually depend on the continuity constant and also E0 E max. We'll write our preconditioner like this A approx tilde and PS, and we'll try to check numerically is working or not. So we'll first take with one parameter just to check that is working or not. And we see for different choice of parameters 0.4, 0.499, 0.499. Again, our iteration count is bounded, it's not growing much. And for different choices, kappa 1, 10 to the power minus 5, 10 to the power minus 10, and different level 5 and 6, we are seeing it's not growing. But secondly, we are going to choose more parameters with this example. And you will see if I'm going to use 3 plus 3, 6 parameters. Again, iteration count is remain bounded from different choices of kappa, nu, alpha, and different level. So what we achieved? So we achieved a computable robust preconditioner with efficient linear algebra. There are 2 publications related to this result. So the next thing that can we drive a posteriori for this. So now we are working on this to drive the a posteriori result, a posteriori estimators for this parameter dependent PD using this some deterministic setting or some sense. Can we talk about the a posteriori? Thanks for your attention.